before we go into infinite series, let's review sequences and series, okay? Before we talk about the axioms of probability. So that will be lecture 0. That is the topic of today. So some of you have taken this class and you know that I give you my last shirt, right? And even this one that I have on me, I will give it to you. I'm very generous. So let me offer to you this gift. So I will give you the equivalent of money contained in those piles. One pile contains 2 to the power of $7. The next pile contains 2 to the power of $8. The next pile contains 2 to the power of $9, 2 to the 10, and on. There are infinitely many piles. I will give you the equivalent of that price if you want it. So please, in your comments, let me know if you want it. Or talk to me.
I'm good.
You're good, huh? Well, you look like you have enough, so I guess you don't need more.
You know, I don't remember exactly how this one goes, but I remember it doesn't end.
Nothing ends well, guys. That's if you're a pessimist. Melissa will pass. Well, Melissa knows me, right?
Yeah.
Today I tried to attack yet another person, right? I have a new German person that came in contact with me. Alejandro passes. Seems like a scam. Well, guys, you can be suspicious of me. That's one thing. You see, you might have taken quite a lot of math classes. The question is, if you pass or not pass, well, that's up to you. That's up to your ability to analyze mathematically. So if you are passing, oh my God, everybody is passing. Erica is passing. It's just, you see, you are swayed by the current of other people that decided not to take my offer. If you are passing, then why are you passing? Wisdom of the crowd. Crowds don't have wisdom. Is it too good to be true? What are you passing on? That's the question. Okay. No, guys, you are. What are you? You grew up too early. What you see? Here is the problem that I have with Americans. They always use the word "it," but they don't know what it refers to. Right? It is what is it? Is this too good to be true? What is it? What's the noun that it refers to? Its value. Oh, Naomi, where are you? I don't see you. I need to look into your eyes. Oh, here you are. Good. Now I can see your eyes. All right. So I guess in the silence I don't hear anything. So let's go about and ask, what are you going to get? You're passing on something. What will you get if you take that something? That's the question I'm asking. Okay, an infinite amount of money, says Syed. So if that's the case, why are you passing?
Well, from an econ standpoint, it would lose all of its value, but I don't know if that's the question
that's
that
not
asking.
my point at all, trust me.
Okay.
Right? I do not like economy or economics. Okay? It is not the reason. It will be worth something, I promise you. Or let's pretend that it will. If you want it, I can give it to you. So let's see, I guess, what it is. You don't seem to be that thrilled. Maybe you took too many math classes, nothing surprises you anymore. So are you going to get something? That's for the first question you should ask yourself. Will you get something if you take my offer? Will you get something? So Melika says no. Probably not. Okay.
Get a negative number.
So let's see what happens if you believe that you get something. So if you get something, let's call it S. That's a something, correct? S is a something. That means that you will get 2 to the 7 plus 2 to the 8 plus 2 to the 9 plus 2 to the 10. And then I use my pattern recognition. I put in parentheses whatever follows 2 to the 7 because it looks like the entire sum. Do you agree? Very little difference, except the entire sum starts with 7. Good. And then what I can do to make it look exactly like that sum, I just simply factor a 2. Correct? I simply factor a 2. So I have 2 to the 7 plus 2 times 2 to the 7, 2 to the 8, etc. That's the exact sum, which is S. So I simplified it to the equation S equals 2 to the 7 plus 2 times S, which when you solve this equation translates to S being equal to minus 2 to the 7th dollars. And unfortunately, nobody decided in this class to take the offer. In my other classes, they tend to be more trusting. That means that if you took this offer, the something that you are getting is $128 as a gift to me. And you should know, of course, that the German word "das Gift" means poison. You should know that's a very good thing. So if a German offers you a gift, don't take it. Good. Now, which, by the way, why am I also mentioning German? You might know, or some of you might guess, that today is a very important birthday. And that birthday is of German Admiral Karl Dönitz. You understand what I mean? That's not a coincidental thing that I mentioned, but yes, it's a code. Karl Dönitz, the U-boat commander, the engineer or architect of the Atlantic War, of the Wolf Pack. He was born today. You can check it on Wikipedia. Good. So, of course, I'm surprised. I mean, you should be very savvy in mathematics. I'm surprised there are no objections. So here is the one objection that you should have given me, right? So, well, look at this equation. What other things solve this equation? Well, if you plug in infinity, infinity equals to 2 to the 7 plus 2 times infinity, correct? So maybe you should have been getting infinity. There is a problem of that, guys, right? So I can tell you several problems. First problem is that this symbol is not a true infinity at all. If you took analysis, if you took it with me or with somebody else, you should know that this symbol refers to, except for complex analysis where it actually refers to a number, but or to an actual entity, infinity refers to growth without bound. Good? It means just that something is having the property of bloating and bloating and bloating and growing without bound. Okay? So if somebody has a pituitary gland problem and they continue to grow and grow and grow and grow, and there is no ceiling that will stop them from that growth, that is the symbol that you use to describe it. So it is not something that you get, okay? You understand what I'm saying, right? The reason you got -7 is that you believe that you get something. If you believe you get something, what you are getting is this. Do you know what the symbol means? Apparently, a lot of people do not know what the symbol means. This means dules makam. Dules makam bedeutet you are getting, well, how should I say, very impolitely nothing, okay? Or something very unpleasant. It's strange. I mean, it's such a nice symbol. It's almost like the flip of the finger, but means something not the same. It's not the same gesture. Good. It means you're getting nothing. So
but this word is not an international word.
What?
This word is not an international word.
Well, it's too bad. It should be international, right? It's with one of my
like dacha.
Dacha? Well,
Like
dacha, yes,
dacha.
it's international word. In general, I feel you will leave my class and you will not know about the marvelous things that I can teach you, right? One of them, I plan to make you read a Dostoevsky novel, the player, right? So you know this Igrok, the player. I have a translation of it. I'm not sure if the translation is good. I read it in Russian, but you might be asked to read it.
But this one about gambling, yeah.
It is about gambling, since we're in probability, must be relevant. Good. So there are many other things. So I will mention that in a little later. I will tell you exactly. Okay. So this is. So listen, guys. So first of all, you might have. I have notes for calculus where I can show you more about it. We'll see if we have time for it. Okay. But there are several things that happen. If you ever solve physics problems, you realize that many of them have infinity as a possible solution. Even if you believe infinity is something, it's a possible solution, which you often, well, not often, you reject it. You understand? Physically invalid. Infinity seems to be something that it's considered that nature doesn't want to give you. Understand? If nature has a chance to give you something finite instead of something infinite, nature chooses the finite. And I can show you examples in my other notes for calc students. I gave a very, very basic example when you consider tension is in the string, right? The tension in the string is uniform. Why do you say it's uniform? Because the string is of mass 0, and it's nearly uniform if the string is close to mass 0, okay? And you cannot push, or you cannot, sorry, pull a string that is of 0 mass with different forces, because that will accelerate it by Newton's laws to infinity, and that's not allowed. You understand? So infinity is an answer that's rejected, and we will go about. This is if you recognize as a divergence series. When you take calculus 2, this is the answer that you give to it. But I will explain why that's the answer that you give to it, and why what I am saying is not a contradiction. In fact, the reason I came up with this problem is a long time ago when I taught calculus 2. There was a student that asked me, how is it possible to have a summation? I think it was a sum of integers, 1 plus 2 plus 3 plus 4 plus 5, and how could that equal to -1 over 12? As soon as he mentioned that, I realized how you can do that with simpler examples, like very basic, simple examples. You understand? I do not know the physics branch in which this apparently is important, but I think in string theory or some other physics branches where you have this summation and its interpretation is -1 over 12. That's the significant interpretation. The fact that it's a divergent series is not a significant interpretation for the problem. Good. So I will explain the notion in which you have to understand this summation, and in which why for our class the answer will still be that sideways 8. Good. But we will get there again. I mentioned my notes. I wrote so much, and for those notes I drew some such nice pictures. Let's begin by talking about sequences. Okay. So you know that a sequence is just an ordering, right? If you ever went to a store in a socialist country, soon you will realize how to do that. You have to wait in line, right? And when you wait in line, you think about a sequence. I am first and you are second, and the guy behind is third, right? And when you really get through communism, that's when the line gets infinitely long. And that's when you have an infinite sequence. It's just a way of ordering objects one after another, after another, after another. Good? So a sequence is defined as a function that orders things from the natural numbers to x, right? And here is an example. So here we have sequences of numbers, okay? So 1/3 is the first number, 1/5 is the second number, 1/7 is the next number, and that's written as a rule by 1 divided by 2 times n plus 1. That's how the integer, the order, is assigned, right? So this is the operation that assigns it. I'm assuming, guys, you took some mathematics. It's not new to you, but maybe there is 1 or 2 students to which it's slightly new. And the numbers 1, 2, 6, 24, 120. Do you recognize this sequence, guys? What is 1, then 2, then 6, then 24, then 120? You might recognize this is just n factorial. We studied n factorials here, right? So you take an integer and you take factorial. So you have an operation that describes how the sequence is built. Sequences can be enormously complicated. Okay. Now, what is it that we mean when we speak of convergence of sequences? Right? You remember we have limits for sequences. And here is a very simple example of what it means for a sequence to converge. It means that the terms, as you go down the n, as n becomes larger and larger and larger, the terms look identical, okay? And here is an example. So what does it mean to look identical? Suppose, if you remember delta epsilon, by the way, delta epsilon arguments I spoke with a German girl this morning, and she studies mathematics, right? She mentions this, and it's a mistake. Whenever somebody mentions they study mathematics, I right away try to invite them to join my class, right? Even if it's in the middle of the night. And she says that in her analysis class, she did not understand fully. It's not intuitive to her. She likes the algebra part, but she doesn't like topology, and she does not like, what was that? No, delta epsilon doesn't seem intuitive to her. I hope to you it seems extremely intuitive. What is delta epsilon idea, right? So epsilon is the resolution of a detector. Okay, how good a detector is at telling when something is or is not a particular value. So for example, you might see that the sequence 10 to the power of minus n converges to 0. Okay, that means 10 to the power of minus 1, 10 to the power of minus 2, 10 to the power of minus 3. It will converge to 0. How do you know that? Well, suppose that if you look at a calculator, you can only see the first 5 digits. Okay, that means your resolution is roughly 10 to the minus 6. It means once it's 10 to the minus 6 and onwards, you do not see the digits. That's why I selected the sequence, because it's very simple to illustrate it. Good. It's important later for probability, because probability is a kind of sequence. Okay, so what we have, we can list the sequence in a column. So this is first row, second row, third row, fourth row, etc. Good. So there is one column and there are many rows. So what do you see? So if you can only see the first 5 digits after the point, then you see that this number, it does not look to the detector like 0, correct? Because I see something other than 0 for this machine. Number 2 does not look like 0. Number 3 does not look like 0. 4 does not look like 0. 5 does not look like 0. But everything after 5, rows 6, 7, 8, all the rows as I go down the line, they all look like 0 to the detector of resolution 10 to the minus 6. Do you agree? And if you, that's the epsilon. Epsilon is the detector that's supposed to tell you whether in this case we get 0 or not 0. So starting from rows 6 and onwards, you get zeros. Good? Guys, so far what I'm saying, am I making sense to you? Yes, fully making sense, right? You have to see that. Yes. Good. So here is how we define a convergence of sequence. A sequence A sub n converges to L if for every epsilon there exists n of epsilon such that A sub n minus L is less than epsilon whenever n is bigger than n of epsilon. And we say that limit as n goes to infinity of an is L. What is it saying? Okay, it's very simple. What it means is this. The sequence an will look like the number L once I start checking low enough rows, right? Once I go down the rows, the terms will look to me like L. Anybody who looks at it will say, well, it scans down the column and starts saying, oh, I just see the same number. Why did you have to write the same number so many times? Do you understand? What is this n of epsilon? That's the first row for which that happens. So for this sequence, n of epsilon is 6. I picked a specifically very simple sequence where you can right away see what's that n of epsilon. It's 6. You understand? Now, for epsilon equal to 10 to the minus 6. You understand? So starting from 6, I don't see it. I just picked a sequence which gives you the same row as the power of the sequence. Okay, but in general, it might not be so obvious. But what it always means is that whatever detector you have, the detector can only identify finitely many of the digits that expand an. Okay, and the detector will eventually stop being able to tell whether you have another number other than what you consider to be the limit. In this case, it's 0. Okay, so the detector stops being able to tell that 6 is not 0, 7 is not 0. None of them actually are 0. The detector thinks incorrectly they're all 0. They are 0-like. In general, if we converge to L, the sequence looks like L. Are you getting me, guys? All right, it's very short review. I do not have too much time in this class. It's just one lesson that I can offer to review those ideas before we talk about probability. Again, sequences, probabilistic sequences are even weirder because probabilistic sequences are not deterministic. You do not know how the columns will look. You understand? I will try to talk about probability next class. Hopefully I will prepare and be ready for it. Today I just scanned it a few minutes before teaching. Okay, so That's what the definition is saying. So any detector will fail to see the difference between the values of the sequence, the actual values, and L once you look down the columns. Down the column, sorry, starting from some particular row, and that row is labeled n of epsilon. That means epsilon is the resolution of the detector, n of epsilon is the first row. This particular fixed detector fails to detect difference, you understand? So it can be difficult to calculate this, but if limit exists, that's how it would look like, okay? Now let's see, there are going to be very important limits. And let's see if you recall how to solve those limits. Important limits, that's the next topic. Do you remember this thing, guys? What is the limit of that expression? Let's see who has good memory, who has taken calculus.
That's E.
Okay, well, okay. That's called Spielverderber, or spoiler of a game, because the others haven't had time to participate. Thank you, Carol. I'm appreciated regardless. That is E. And if you thought anything other than E, then you're in the right place. Well, actually, well, you should be not here, but I will make sure that we'll carry you along. Okay. So this limit comes from, if you remember the differential equation, how do we solve the derivative of a function equals to the function? In other words, how do we find the fixed points of the derivative? Fixed point means the fixed function, right? Which functions are not moved by the derivative? Think of the derivative like a ghost. It comes around and it smashes poltergeist. It moves things around. Well, if you're not a mathematician, you pay attention to the things that were thrown around. But if you are a mathematician, you pay attention to the thing that stayed in the same place, that was not moved by the ghost. Okay, so what things are not moved by the derivative? Well, I realized by playing around with functions of the form a to the x that their derivative, well, this is the definition of the derivative, limit as h goes to 0, a to the x plus h minus ax over h. I realize I can factor out the ax, and I have this limit. Do you see that? And I look at this limit. This was the general derivative at some general point for the exponential function. And I realized that to find the derivative for the exponential function, I just have to find its derivative at the value 0. 0 is somehow very important for the exponential function. The derivative exists as soon as it exists at 0. You understand? That's not true for most functions, but it seems to be what's happening with exponential functions, and I get this limit. Good? I get this limit. I do not yet have any way of evaluating it. It's not an easy limit. That's the first limit if you are taking Calc 1 with me and you're watching this lecture. This is the first limit that's very non-trivial, highly non-trivial, not like the others where you can just plug in or figure something very simple. So this limit, you can play with a calculator. That's not really a way to convince yourself, but maybe if you believe in the calculator, then you will see that if you select a equal to 2, this limit is going to be a number below 1. And if you select 3, it will be above 1. And you can just play around between 2 and 3. You can make this limit look more and more like 1, which is then, you see, that would then be a function whose derivative is itself. Because if c is equal to 1, c is this value, right? Then the function is not changed. Good. So then you define, it's not a definition yet. You can say that e to the h minus 1 over h, e is just going to be that number that hypothetically will give you the limit 1. So before I continue, are you more or less with me, guys? What I'm talking about? It's a review. I'm not, obviously it's not a good first description. So far, so good. Good. Mm-hmm. Okay, so this implies that the derivative of e to the x is equal to e to the x. Good. And I'll show you a pretty clever idea of how you can just play around. You know, you have to really play around with your derivative. If you're bored, you play around with derivatives. So what does it mean for the derivative to equal to itself, to the function, right? So the derivative of function to equal to the function. It means that, well, if I take the limit by definition, is that this left side equals to the right side. Good. Which, if I, what is this h? It's just saying that if h is really, really close to 0, then this quotient is very similar to the function fx. Good, which means that f of x plus h minus fx over h is approximately f of x. Good. If you guys have any questions, you ask me, correct? And for Milika, I believe for you it's right now very strange, very wild, but it will be later when we talk about it in Calc 1 that it will make far better sense than it makes right now. Some lectures forward, it's possible to still, if you understand the summation part, it's still possible to understand much about probability, but those limits do eventually play quite a big role, starting especially from chapter 4 in our textbook. Okay, so look at this expression. I can rearrange it and I can solve for f of x plus h. It's approximately equal to 1 plus h times f of x. You understand? I multiply by h, I move things around, and I can make f of x plus h approximately equal to that expression. And that gives me an idea. I can use recursion. You understand, right, guys? Recursion. That means what? That means this is just a number. F of a number is essentially 1 plus a step times the number minus the step. So that's a recursion. When I move a step back to evaluate where I'm currently, that means I'm using recursion, like I did for that problem with counting piles. Remember, we had a bunch of piles with non-identical objects in the pile. So like, let's say if I take a crowd of students and I divide them into groups, and some groups might be groups of lonely people. So maybe one person and not more, and other groups can contain as many as you like, okay? So it's a recursion, same idea. Are you with me, guys? Everything I said so far, I make sense to 98% of you at least, yes? Good, so let's going back by a step. What happened here? Okay, thought somebody asked me something. Okay, good. So this is my recursive step. F evaluated at a number is 1 plus a step, F evaluated at x minus a number. So if we have e to the x, we know one value at which it's easy to evaluate, that is 0. At 0, it's 1, correct? So we can take the interval from 0 to x and break it into many tiny steps. So the step is going to be the length of this interval divided by n, and n is huge, n is million, because you see, this is not a full equality. I need h to be very small. I need it to be microscopic for this expression to be true, for the quotient to almost equal to f of x. H has to be very close to 0, so it has to be microscopic, right? So it's h is equal to x over n, and then here I take the step. So I take a step back. Basically, I will take n steps until I get to 0. Understand? So if I fix n as very large, and then I just have to take n steps. So let's take those steps and see what we calculate. Are you with me, guys? You understand how I got this step? So I have f of x. What is f of x? F of x is 1 plus the size of the step times the function one step before. And what is this expression? This expression is just multiply by an extra 1 plus a step, and you can move a step back. So that's why we have a square here. You understand? Because we had this 1 plus a step, and then I move one step back. That's the same as multiplying by 1 plus x over n. And moving another step back. Then I move 3 steps back. Yes? And then eventually I move n steps back. Are you with me? So you see, what is this? This is 0. Do you agree? Because x over n, move n steps back, you get to 0. So what do I get? I get that f of x is approximately 1 plus x over n to the power of n, the function evaluated at 0. So if you're right now taking Calc 1, we will actually be doing that in Calc 1. We will examine this limit as soon as we talk about the exponential function. We still kind of keep it safe. So that will happen within the next month, I think. So do you understand what I just got? I got 1 plus x over n to the power of n. It's an approximation, you understand? I mean, this is not rigorous reasoning. You can find all sorts of problems. Maybe the mistake builds up and accumulates to be something significant. It's just what you do, you play with it, and it gives you an idea of what an answer might look like. It's not a rigorous proof, but it has something else. it has the essence of the idea. Why would you think of such a property? There, I have two ways of explaining why would you think about it. I really like this one. Do you understand? And then you think if I make the steps smaller and smaller and smaller still, that is, if I take n to infinity, n has to be larger and larger and larger, that would be perfect, right? So what I see is that e to the x is just the limit as n goes to infinity of 1 plus x over n to the power of n. It happens to be this exponential function. You follow? So now a few simple examples. What is, just quickly solve a through f and tell me what are the values if you can. And if you want me to go over this explanation one more time, just let me know. The notes are posted. So all of it, guys, is just a review of Calc 1. So if you're taking Calc 1, you will see this very soon, if you're just first starting it. Let me know when you're ready.
For the third one, is the exponent 1 over h or 1 over n?
For the third one, for C, what's the third one here? You mean C or you mean
C.
C? That's 1 over h, of course.
Okay, thank you.
H goes to 0. All right, so let's solve it together. This is again, right? So first part is very simply, right? So we have figured out, hopefully, that if I have 1, plus x divided by n to the power of n, the answer is e to the power of that x. So since the x here is 1, part A is e to the power of 1. Part B, in this limit, I'm subtracting 5, which means I'm adding minus 5. That's my x. It is e to the minus 5. Now for C, just to humor you, I will do it one more way. So notice here that I no longer have an n. It's no longer a sequence. Those are limits of sequences, but C, h is just a real number approaching 0. So the pattern that you should observe is this. If you have 1 plus a number that melts to 0 to the power of 1 over the same number that melts to 0, you will get e. That's if the number melts to 0, that is if the box is very close to 1. This can be derived possibly from a sequence, but let's just do it one more time. Let's do it a different way. You do remember logarithms. Logarithms are inverses of exponential functions. Something that you realize it's really the same, it's the other side of the coin. If you know exponential functions, inverse functions have derivatives that are immediately relatable. And basically properties are very similar. So in Calc 1, again, I speak about the geometry of that. The derivative of ln x of the natural logarithm is 1 over x, correct? And that means that the derivative of ln x at 1 is just 1 over 1, which is 1. By the definition, if you take the derivative of the logarithm, you will, at 1, right, you will have this limit. Okay, we know this limit to equal 1 already because we have other techniques to figure out that the derivative of logarithm is 1 over x. And if I do it at 1, the derivative here is 1, right? So I take this, and then ln of 1 is 0, so I have 1 over h times ln of 1 plus h. And logarithms have this nice property that I can take an expression and I can put it in to the power. So I have that limit of ln of 1 plus h to the 1 over h. The limit is 1. So I can now take exponentials of 1. So exponential of 1 equals to the exponential of the limit. Factoring out the limit, the exponential cancels out, and I get this expression. So this limit equals 1. So of course, people that haven't taken calculus do not understand anything I said here, but you have taken most of your calculus. So do you understand what I explained? Any questions? This is easy so far, correct? Cool. If not, guys, if there is anything I can add or help you with, just let me know. Okay. There is still time again to pick it up. It will become relevant, extremely relevant by the time we reach chapter 4 in the textbook or the equivalent material, but we are only beginning chapter 2. So still it's going to be fairly basic. Okay. And then from there, I use this wishful thinking. Okay. You see, I realize what does that mean? There is no h, or this is just a literal understanding. There is just, you don't need a letter, you just need to realize what this is saying. If you have 1 plus a number that melts to 0 to the power of the same 1 over the same number, the answer is e. Okay, so here I have 5h. Okay, and here I have h. So you see I have this pattern, but this is incomplete. So what I do is I insert 5 by wishful thinking. This box and that box have to have the same value. Good. I insert 5 and I cannot change the expression, so I multiply by 5, and now I see that this part here is just e. You see the thing that I'm circling is e, and to the power of 5 is e to the 5. Clear? Do you understand how I got e to the 5? Just by pattern recognition. That's one thing you develop. It's just this box and this box have to be containing the same expression that goes to 0 at the same rate. Now, what do you do here? Here you have minus 2h. That's the same as 1 plus minus 2h in a box. And here I need to insert minus 2, and also therefore to the power of minus 2. So the expression circled here is simply e, and this is e to the minus 2. Good? And in general, limit as 1 plus x to the h to the power of 1 over h, I need to insert an x here. So that would be, oh, I didn't complete it. It will be e to the x. Right? In my notes, it's e to the x. You understand. I forgot to put it in. All right, so back to somewhat simpler things. So something that hopefully you can understand without any prior knowledge. Let's talk about series. So if you have a sequence, we can add it up. And what the infinite sum is called a series. Now, the meaning of it, as we take in calculus conventionally and in our class, the meaning is that you take partial sums, right? So the way you add it is not like I offer to give you the money right away, the equivalent of the piles right away. Here, I give you first pile, followed by second pile, followed by third pile, and onwards, right? So then this is the way the summation is going to work. Partial sums means you first get this, and then you get this, then you get this. You understand? It's a sequence of partial sums. So you understand it as a limit of the sequence. You go down the column until you get to the value s, and that value is the limit of the sequence if it exists. In other words, if the rows start looking alike, just like with the sequence, if they start looking like the same number, then I say the series converges. So I translate convergence of series to a convergence of sequence. Okay. Again, I am emphasizing very different from the way we try to think about the summation. My offer, my generosity of giving it to you right away. Okay. Here I give it like this. First, I push to you first pile, then I push second pile, then I push third pile. I don't inject it all at once, and there is a big difference. And I will show you today, perhaps, why there is a big difference. If we still have time, I will go to the other notes and I can show you why is there a difference, okay, between the two operations. So the limit of the sequence, the value it's striving to is, if it exists, will be s, which will mean that the rows will look alike. Everybody understands what I mean by partial sums. So back to that problem, right? It was 2 to the 7, 2 plus 2 to the 8 plus 2 to the 9. So I can offer to, this is going to work like this. First, I give you 2 to the 7. Then I give you 2 to the, I give you 2 to the 8. Then I give you 2 to the 9. So what you're having finite additions of money. So you have 2 to the 7, 2 to the 7 plus 2 to the 8, 2 to the 7 plus 2 to the 8 plus 2 to the 9, on and on and on. Yes? And so here is our first important condition for convergence of series. Here it states that the summation, if it equals to s, that means the limit equals to the limit of the partial sums equals to s, which means the terms that I'm adding have to be zero, essentially zero. That makes pretty much sense. You agree? If each time I'm adding a very big term, I will definitely detect a difference between previous pile and my next pile. Assuming, of course, my detection is not relative by the size of the pile, right? It just up by absolute amount that was added, I will feel it. It's like, imagine you're holding some weight. You're Atlas and you're holding weight. If I'm gonna drop metal bricks onto your plate, onto the weight that you're holding, you will feel every extra pound, right? So you would feel it getting heavier. You will detect increase in heaviness unless, of course, the piles become so very, very thin. So one consequence is that unless the terms of the sequence converge to zero, the series has no chance of summing up, of conversion, okay? And here's how we prove that. Very simple. It's the divergence test, right? We have that the a sub nth term, it's just the partial sum up to the nth term minus the previous partial sum. Do you agree? Okay, so I be sure I think I make sense, but only to myself. Do I make sense to you? So type if I make sense to you, please. Say yes or speak to me so I know that I'm not going faster than I have to. Okay. Good. So this is what I get. Now what's the limit? the limit of a sub n is the limit of the difference. You understand what's the difference, right? And what is the first guy? It's the limit of the difference is the difference of limits. The first guy is approaching s by assumption, it converges. The second guy approaches s as well. So s minus s equals to s, so it's a 0. So here is one thing. Do you understand that s of n minus 1 is just the term of the sequence that lags 1 unit behind? So if n goes large, then the one behind it is pulled lower. You agree? You see, this is what I imagine. I imagine Sn is here, and Sn minus 1 is just immediately on the row above, and I'm going like this, right? So what happens is that the rows, they become like S. So clearly both this row and that row will look alike, so the difference between them will look like 0. You understand? That's why the limit holds. It's very, very trivial. It's just like you're going through your accounting list, and in your list, the rows are alike. They are too alike for you to detect any difference. And the difference between them is the term of the sequence. So it has to go to 0, which clearly does not happen when I have 2 to the 7 plus 2 to the 8 plus 2 to the 9. Do you agree? The thing that you are adding actually approaches infinity. Are you with me? You agree that 2 to the 10 is much bigger than the previous term. So it's actually, even the sequence itself approaches to infinity, and clearly the summation will approach to infinity. That's obvious, right? So as you're adding consecutively, you are accruing money. So in your calculus 2 class, so never blame me if I said the answer is minus 128 and the teacher tells you no. That's because the teacher and me, we're talking about entirely different things, okay? The limit is growth without bound in this case, but that does not mean, and I will show you hopefully today, a paradox that really makes this very strongly felt. Okay, that there is a huge difference between approaching somewhere and being somewhere, right? It's like when you're jumping out of the window, you are approaching death, but you're not dead. Very huge difference, right? So you're still functioning, still alive. It's not the same. Good. So the answer would have been might be something else if I give it all at once, but if I interpret addition as a limit of giving you one pile, another pile, so as you accrue the piles, you are actually gaining money. So the simplest series is perhaps of this form, guys. Simplest series is geometric series. You can see this is how it's written in summation form, but you can also think of it like this. It plays a huge role all the time, and it will play a huge role in probability, okay? Okay? So it's easy to see if you took calculus that it actually is convergent. The series is convergent in our ordinary sense of the word, in our calc 2 sense of the word, if this radius, this thing that I'm raising to higher power, is between -1 and 1. Okay? If that's true, the series is convergent. But you don't actually, in our class, you will rarely have to worry about convergence. You will frequently just have to figure out what's the sum. In probability, you often will have to deal with series that you can pretty much be sure they converge, but you just have to deal with the sum. Okay? So here is how we can figure out a summation of a geometric series. You with me, guys? So we have we can again isolate the tail of the series after the first term, because it looks very much like the entire thing. And then I can make it look exactly like the full thing by factoring out, in this case, an R. Okay, I factor out an R. We have the summation, and what you see in parentheses here just becomes S. I have now a simple equation. S equals to AR to the M plus RS. I can solve it. It's just now simple algebra, and I get this solution. You understand? So I'm not sure how you were solving series when you took calculus, but here is a very quick way, right? They just right away, you can just not even remember anything. You can see what the summation equals to. Here in the formula, you can see why I don't like 1, right? If R is bigger than in magnitude than 1, then you see that the terms of the sequence will bloat. So it cannot converge based on the divergence theorem that we have above, right? Because if we sum partially, the limit of the sequence that I'm adding has to crash to 0, has to melt to 0. So again, I mentioned the limits at infinity is the topic that we want to talk about. Okay, let's see. We finish at 6:50, correct? I just wonder, maybe I will show you a few things before moving on about geometric series, just to be sure that you can sum them up. So, and here are the notes I talk about. They are actually under Math 150, Calc 1. So limits at infinity 5. Okay, you understand how to find them, correct? So here is one example where infinite series, geometric series, in fact, you have used all the time. So you have 1/10 plus 1/10 squared plus 1/10 cubed. This clearly sums to 1/3. How do you know? Very simply, you can, oh, sorry, not this, the next one sums to 1/3. I said something incorrectly, right? So this one will sum to 1/3 because what is 3/10 plus 3/10 squared plus, like this, you see the 10 powers are increasing. You can just do this, right? So you take the first term, you keep it separate, you put in parentheses everything else, and you factor out 1/10. You understand why I factor 1/10? Because if I factor out 1/10, this will start from 1, then it will go to 2, 3, and onwards. So I factor out 1/10, this now becomes exactly S, and I have S equals to 3/10 plus 1/10 S, which is equal to, when I move this expression to the right, I have 9/10 S equals to 3/10. And so S equals to 1/3. Okay, here is one example where you don't understand probability just yet, but here is, let's see how quickly you can do that, guys. So you have one roll, one die, and you roll it until either the number 1 or the number 6 comes up. Okay, if number six comes before 1, you win. You understand? So you roll, and the termination is when you either have 1 or 6. As soon as you got first 1, game over. Or if you get first 6, game over. Actually, you win the game, right? If it's 6, you win the game. If it's 1, you lose the game. So I'm asking this question. Let's see who has good intuition. What's the answer? What's the likelihood that you will win? That's my question. Okay, interesting, Kazi. Okay, think about it for a moment and ask yourself, what's the probability that you win this game? And if you want to calculate it, I mean, we're still doing it very informally, correct? So next class, it will be probability. So Paula says 1/3, Kazi says 1/2. Okay, Valeria says 50%, Gabriel 0.5, which is the same. Okay. Bowen, I'm not sure what you mean 2 to 5. So you don't stop rolling until you get either 1 and then the game stops. First time you get 1, you stop, or first time you get 6, whichever comes before, right? So 1 or 6 are both codes to stop the game. If it stops with a 6, you win. If it stops with a 1, you lose. Good. So this was a very, very easy question. Yes, okay, which you don't need too much knowledge, perhaps, right? So you think of it, okay, the die does not care where to stop, either at 1 or at 6, right? So those are equally likely options for the die, since if you don't care, like many of you don't care, when you don't care, you can either do one thing or another at equal likelihood, you understand? That's what not caring means mathematically, is that you don't have a preference for one action to another action. So the die, if it is a fair die, has no preference whether to end the game with a 6 or to end the game with a 1. Do you agree? You see how I'm thinking, right? So you start thinking about justice. Once you get old and you realize that people don't care, you realize what it means. It means that the probability is pretty much like noise. Okay, so that means that the answer has to be 1/2, and many of you saw it very fast. You might have very good intuition, probably in different people, so you know how it works. Yes. So here is the infinite series way of solving this, okay? Which is, of course, for this problem much harder, but the idea was to illustrate how they arise, okay? So you imagine that you win the game. If you win the game, you can win it on the first roll, or on the second roll, or on the third roll, fourth, fifth, etc. Yes? So this is the situation. So WK means win on the kth roll. What's the probability of winning on the kth roll? It means you have 1 place, 2 place, 3 place, k-1 place, all the way to kth place. All of those are neither 1 nor 6 because the game did not end before you reached the last kth roll of the die. And then the possibilities here, that's where we begin counting, right? How many universes for the die to not produce either a 1 or a 6? There are exactly 4 possibilities, 4 possibilities, 4 possibilities, 4 possibilities, yes? And on the bottom, you imagine you allow the die to do whatever it likes, right? So you count all the universes. What you do when you calculate probabilities, you count all universes where you consider that you want to end up, divided by all possible universes where you could end up. And so you are doing a double, you see? Each probability question is a double combinatorial argument, one for the numerator, one for the denominator. You're doing 2 countings, right? So here it's 1 box here, 1 box here. So here you have 6 possibilities, 6 possibilities, 6 possibilities, 6 possibilities. The last one, only 1 that you want, only 1 universe. So the last box is only 1 possibility and 6 possibilities on the denominator. So we have 2 Kafka procedures, 4 to the k-1. This would be 6 to the k-1, which I can group together as 4 over 6 to the k-1 times 1 over 6. You understand? That is my probability of winning it on the kth trial. And then the probability I win it altogether is the summation to infinity, because I might win it on first trial, second trial, third trial, etc. So the answer is this: 1 over 6. That means I win it on the first trial, plus 4 over 6. I did not win on first trial, times 1 over 6. I won on the second trial, plus the next term, plus the next term, plus the next term. Do you understand? So here, what I need to do is just simply look at it. It will be the same series if I just factor out 4 over 6. Do you see that? So probability equals to 1 over 6 plus 4 over 6 times probability, and I can solve. It means 2 over 6 times probability equals to 1 over 6 probability, and that gives us probability equal to 1/2, which of course we knew with a much simpler reasoning. It's always good to have several reasonings, but what's actually happening is perhaps an infinite series. That's just an illustration of where it will be might play such a prominent role in probability, this type of idea. Good. And here is one thing that's pretty interesting, guys. I remember hearing about this question a long time ago. Later, I realized it's a pretty famous problem. Okay, and here is that problem. You have 2 cyclists, and they are 20 miles apart, and each is riding towards the other, like I'm showing my fingers, at 10 miles per hour. Yes, on the nose of one of them, there is a fly. Immediately when they start the trip, the fly takes off. It flies at 15 miles an hour from the nose of one bicyclist to the nose of the other, back and forth, until the bicyclists really touch noses, like this, right? Until they touch noses, the fly is just gonna jump between them. The question is, how much distance will the fly cover? That's the question, okay? So that's a very famous problem. You can think about it. Probably I will not give you too much time today. I might not even give you the answer, right? So keep excited, so to speak, right? But I remember how I solved it for the first time, and I was very proud, or maybe very ashamed, that I solved it like the great mathematician von Neumann. So Kazi says 12. No, Kazi, it's not 12. My apologies. Okay. You understand what I'm saying, guys? You think about it, I solved it just like von Neumann, except it took me much longer. Von Neumann solved it in a second, right? And using a very terrible way of solving this problem, right? Like using the dumb smart way or smart dumb way, I'm not quite sure, right? So, you know, you might realize that it's a geometric series, right? That's how I solved it. I realized, okay, it's a geometric series. So von Neumann goes, he was a Martian, right? He was just a brain, like this. And actually, I have a video translated from his, you know, I tortured my students because I didn't like them. I had to teach a very poor math class. So I figured they don't like me. I'm going to make them watch a movie with subtitles, which they hate, you know, they hate it. So I was writing subtitles. I hate writing subtitles, but every time I write a letter, I think that's just something else that they will suffer again and again. It's called, the class was called Thinking Mathematically. So it was about von Neumann, right? Prophet of the 20th century. I will send you the video so you can watch it. Okay. It took me, I think at first I started translating, I thought it would be fast. I realized how terrible is the job of people that write subtitles. Altogether, probably took me, I would say 72 hours at the very least to write the subtitles. I didn't do it right away. I actually already started in one class and then I finished once I started teaching another class of the same type. Those were terrible students. So if I ever teach it again, I have weapons. Okay, so this is the picture that we have here. We have cyclists and they go at each other, and there is this fly that will take from the nose of one to another. I will not reveal the solution, guys. I will just rightly just brisk through it like this, so you can understand how my solution looked. Right? I don't remember if I use the same notation, blah, 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 right? This. And now let's talk about the next question. Okay. For calculus students, maybe we'll see if they're interested. Again, the point is it's so exciting. Geometric series are everywhere. Now, another question is, I'm not sure, I'm not really a very technological person. My brother got me actually a pretty good thing. Maybe it will help me teach, but probably I can, so what is it? Something like this, right? Maybe I can use it, you know, to better write or draw while talking to you. Although I probably will use it to break nuts, you know, because I'm really very stupid with technology. So apparently cell phones, they have this type of fractal antenna, right? And, you know, my brother, yeah, it's like the reason there are some videos recorded is because I was mentioning, oh, I'm getting old and life is over and there will not be even memory left of it. So I said, just record yourself, right? Just record this. So I said, I don't want to record myself. So he came and recorded some of my lectures, which are posted on YouTube, all right? You can see that there is one first lecture where I'm happy and then years passed and right away you see, my God, it's a different person. So anyhow, so I was teaching it. And my brother once said, oh my God, I'm interested in infinity. Will you help me? And I thought, oh my God, I'm not going to teach my brother, right? That's very, very impressive. So he took me on a drive for 2 hours upstate, parks the car, and what he did, he bought an Infinity IQ 30. It's a 1999 or 2001 car for $200 something. And he just made me drive the car we came with back. That was his help, right? And for that car, he bought a fractal antenna. Since it's infinity, it just goes well with a fractal antenna, which apparently you have in cell phones, or at least had in cell phones. I'm not sure what they use now, okay? I can show you pictures where they use it in cell phone. And here is how this antenna is produced. Oh, Steven, that was your first car. Well, every car that my brother gets, you might say it's his last car, right? Or at least the car is basically whatever he touches, it turns to dust. So so we have this is the way you build it up. Okay, so you take I'm not gonna teach you why this works, why it's a good antenna. That's beyond our class, and actually myself I don't really know fully. You need to know electronics, but I can tell you how to be very rich. Okay, so what you do is you take this metal panel, okay, and you divide it into 9 squares, and you puncture out the middle square. So this is of, let's say, this is of dimensions 1 by 1. So you puncture out 1/9, correct? And then the next step, what you do is you take every one of the remaining squares and you puncture out the middle. It's now 1/9 of a 1/9, so it's 1/9 square. You understand? And then you take the remaining ones here and you puncture them, and you calculate how much. But basically, the question is, how much material do you have to use to build this antenna? Do you understand? How much material do you need to build this device? What do you think? How much material do you need for this device? You know, you do it ad infinitum. You divide whatever remaining rectangles or squares that you have, and you puncture the middle square. Does my question make sense, guys? I'm of course trying to move fast because I probably want to go back to the other lecture to be sure that you know something about the Taylor series. Six over 9, Kazi, you mean is how much material is used? So how much material is removed, right? We can know whatever material is not removed is what we used for the antenna. Do you agree? So first we remove 1/9. Next we remove how much? We remove 8 9 squares. 8 over 9 squares. Do you agree? Because we have 8 boxes here and we remove the middle. So first is 1 over 9 plus 8 divided by 9 squared. Can you guess how many we remove in here? So here we remove 8 or 9 cube. Here we have another 8 9 cube. Here we have another 8 9 cubes. So how many we remove together? How many do we remove of the small squares that I draw here?
64.
64 over 9 cubes. You understand the pattern? And the next, of course, it follows by the same pattern. Okay. So how much material do I remove? I think you know series, guys. I mean, I thought you knew it. Kazi, when you put a number n in the power, n is meaningless, right? You remove some amount. N is not an amount. N is just a letter. It just indicates when you use, guys, when you use x or an abstract expression, you are talking about a general, right? So when I say x, that's to me a general person. Okay. So when I say humans are cruel, right? Then I mean every single thing that is a human is cruel. Okay. Zero, Naomi, what do you mean by zero? Is how much I remove or how much remains? Remains. Wonderful, Naomi. So here you see what the solution is. The solution is just a series 1 over 9 plus 8 over 9 squared plus 8 squared over 9 cubed plus 8 cubed over 9 to the 4th. And then very easily, what do you do to figure out the solution? Well, you put the second part in parentheses, and then you realize all you have to do is to make it start with 1 over 9 in the parentheses. Look at it. Here it's this is the first term in the parentheses, second term, third term. All I need to do to start it with 1 over 9 is factor out 8 over 9. So it's 1 over 9 plus 8 over 9 times the amount here in parentheses, and you get the equation A equal to 1 over 9 plus 8 over 9A, which means when you move it around, it's 1 over 9A equals to 1 over 9, or A equals to 1. You remove all the material, which means all you have to do to be rich, it's an expensive device. It costs at least $39, right? Just take one, you can start, you see, an American dream is possible. Start with 1 square metal, puncture this out, sell the antenna, melt it, and start again the construction. Just always melt the same amount of metal into a box and puncture it out and build antennas on and on and on and sell them. Good? You follow? I told you how to be rich now. Let's go back to my other notes. and talk about the Taylor series, a very important topic indeed. All right, a Taylor series, guys. So yeah, I have only officially only 4 minutes, but if you can wait. If you have to leave, you have to leave, okay? So this is the situation. The simplest operation that you have ever encountered, you encountered in the first grade, it was addition, subtraction, and multiplication. Now subtraction, let's say if I take 5 minus 2, it's the same as 5 plus the number minus 2. You understand? So once you realize that there is an entity that's called negative numbers, you can imagine that subtraction is the same as addition, okay? So then you have multiplication and addition. That's for me to just say it simply, okay? So those are the operations that are simplest, but then you begin having more complicated operations like square roots. So sometime in school, you are calculating square roots, okay? But, or even integrals. Maybe last semester or a few semesters ago, you were calculating integrals. By the way, you remember integrals are just complicated sums, right? Just sums with a limit. So really, all those operations, when you understand them, you refer back to addition and multiplication. That's really, whenever you do any calculations, you think about it. Can you name a calculation other than guessing that you carry out that's not multiplication and addition, an actual calculation? And machines, apparently, when you press in calculators, machines are able to add and multiply. Well, they add, and addition can generate multiplication, okay? So then we realize that the type of functions that's simplest is called polynomials. And what are polynomials? They're just functions that involve, once you put something in them, involve only the operation of addition and multiplication. So far, so good, guys? You understand? You had all those stupid definitions in school. Polynomial, it's whatever form, right? But polynomials are just operations that only require the use of addition and multiplication. Good? And then you realize after thinking about it, so what you do, right? You put an input into the function, and then you begin digesting the input. Yes? You begin digesting this input, and what do you get? You see that the input is sometimes not used, sometimes it's used once, sometimes it's used twice, 3 times. So you can then, because addition and multiplication are commutative, I can group based on the number of times I use the input, right? So here I did not use the input, that's the constant term. Here I used the operation by the input once. Here I used operation by the input twice, multiplication by the input twice. Make sense? So every time I multiply, whenever I have an operation that involves addition and multiplication, I just keep track. How many times did I multiply by my input? Okay, this is an operation tells you what to do with x. And then I just regroup. I just rewrite it so that it's grouped neatly. So this is the set of all operations where I don't need the input. This is the set of the operations where I used it once, twice, all the way to the n to n times, right? X to the n. Make sense? Try to play with this game. If it does not, it should kind of be intuitive to you that just any operation that you just write using x, any addition and operation multiplication operations. You can, let's say, have x minus 10 squared. That means x minus 10 multiplied by x minus 10 plus x plus 17 plus, I don't know, x multiplied by x plus 5, right? So when you expand it out and multiply things around, you can group it based on how many times x was multiplied by itself. That's just a stacking, right? Just and then because operations are commutative, I can just carry it out. Good. So that's what is a polynomial. Good. So now next question, guys, is root of x a polynomial? And if not, first of all, what am I asking? I'm asking, is root of x a polynomial? What am I asking? So it's not a stupid question. I hope you understand why it's not a stupid question.
Are you asking if
No.
square root of x can be broken down to addition and multiplication?
Yes, that's precisely right, Shutaro, right? I'm asking very simply, can I model the operation of the square root only using addition and multiplication? And when you press the root of 5 in your calculator, the reason you get a number, guys, is because if you believe that. I mean, I'm not a machine expert, but apparently what are calculators? They're adding machines. So calculators can only perform addition and multiplication. Yes. So you can shake your head like this or like this. It's up to you what you do. Is root an operation that's a polynomial operation? Monomial, by the way, just a particular polynomial. Just in school, they throw a lot of terminology without any meaning. Monomial, trinomial, blah blah blah. What is a polynomial? It's just the operation involved for digesting of the input is just multiplication and addition. Subtraction is addition of negative numbers. Good. So is root of x a polynomial? And if yes, why? If no, why? Okay. So I'm a bit impatient as we have to move. And the answer is no. Now, why is the answer no? It's because of a very simple, simple logical reasoning. There is the simplest one, right? Suppose it is, and again, I mentioned finite polynomial, right? Suppose I can model this process using finitely many additions and multiplications. Now, the function that uses only finitely many additions and multiplications can work on any number. Do you agree? So addition and multiplication work 0, negative numbers, positive numbers, and whatnot. But root does not work with negative numbers. I can give even better explanations. If you have objections with that, I can give you a more complicated explanation. But you understand, I realize that root of negative numbers cannot be taken. That means that root do not digest negative numbers. If they were represented as polynomial functions, they would be able to digest any number. Good. Do you understand how I reasoned? I just know that any creature that can be just represented by addition and multiplication can digest any number, but roots cannot digest any number. Therefore, it's not. But again, in particular, it is not a finite polynomial. Okay, not a finite polynomial. There is a big difference. In other words, I know that I cannot represent root of x by finitely many additions and multiplications. Maybe I can do so if I use infinitely many additions and multiplications. So again, guys, the usual class time is over, but I will carry on this lecture until I finish this topic so that we can begin probability in the next class. And if you have to go, I do not get offended at you. At least I will not show it. So then we have this thing, a power series. It's again an unfortunate name. What is a power series? It's merely an infinite polynomial. You understand? I here do not stop. I mean, I rearrange the terms. And yes, I rearrange the terms and I group still based on the powers of x, assuming that's possible. Okay, so this is operations involving possibly infinitely many additions and multiplications. Okay, and you call it a power series in your books, but that belies the fact that it's just still a polynomial that's infinite. That's all. Okay. So here is my main problem for today, because e to the x is such an important function. So suppose I want to represent e to the x as a power series. In other words, suppose I want to model what e to the x is doing to its input using addition and multiplication. You might already think that e multiplied by 3, it's like e multiplied by itself 3 times. That's true. But what is e to the power of pi? Okay, so that does not look like multiplication to me. Understand? So I want to represent the operations only using addition and multiplication. So what I try to think is this, right? Imagine that this function does equal to an infinite polynomial. Okay, imagine it. So if it's a finite polynomial, that will be shown. You understand? If it's finite polynomials are contained within the set of infinite polynomials, because I can just take the remaining coefficients to be 0. Good. So suppose it is some kind of polynomial. Then how do I discover what are the coefficients? What's a0, a1, a2, and onwards? How do I discover that? Well, the easiest to discover is what's a0. You agree? I just plug in 0 into the function. Remember, this function at 0 is very easy to evaluate. E to the 0 is 1, correct? So I plug in 0 and I get that f of 0 is equal to a0. Yes, the first coefficient. Now, can you tell me how do I get to the coefficient a1? Can anybody take a guess?
Take the derivative.
Thank you. And who said that? Sure. Okay.
Yep.
Yes, you take a derivative. Do you understand why you take the derivative? You realize that assuming derivatives work as they do, you don't have to see there is all this complicated theory which you can build afterwards. You can have this doubt afterwards. First, you are young and you believe in yourself and you just feel that it can go through. It just feels like, well, it's natural to do it, right? And just do it. That's why you're able to do so many dangerous things. You just don't realize how dangerous they are. Yes, Germans are not spontaneous. They don't do that. So they want to talk to me, but they don't share their numbers, some of them. Anyhow, I'm sure they don't understand what I'm talking about. But after being, isolated from you for 7 months, I probably lost my mind entirely. So anyhow, so here we have this situation. So I take the derivative, and then that brings a 1 forwards. Yes, it brings a sub 1 forwards, and I took the derivatives imagining they work as they should, and then I plug in 0. You see now it's isolated. I plug 0 and I can snap it. So f prime of 0 is a 1. Good. And then in general, how do I get to the third coefficient? I need to take 3 derivatives. You see, derivatives exhaust the powers of x until there is no x. Then it isolates the coefficient plus the thing in front of it, right? So look at it. This is 2 factorial. Now to get to the third coefficient, I need to take 3 derivatives. That will make it 3 times 2 times 1. It will make it a 3 factorial. I hope you see that. So in general, if I take the kth derivative, I will isolate the a sub k, but it will bring first kth power, then k minus 1 power, then k minus 2 power. It will basically create this coefficient, which is not, I need just the ak, but it creates ak multiplied by k factorial and a bunch of others that have an x. So once I plug a 0, I get that it's k factorial times ak. Okay, and that tells me that the coefficient that I'm interested in is the function, derivative of the function evaluated at 0 divided by k factorial. And therefore, that's the Taylor series form. You understand? That's the Taylor series form. Whenever you represent a function as an infinite polynomial in x, then this is the coefficient that you have over it. You take the function, take a bunch of derivatives of it, and evaluate them at 0 and divide by k factorial. That's, guys, extremely important. I'm talking about it very fast. I think I have an ability to explain that fully. So if you have never covered it, I can explain. But you need to trust me. Now for e to the x, the derivative of e to the x, it's like water from goose's feather, right? Как с гуся вода, it doesn't affect anything. It remains e to the x, okay? Which is very nice. Then I can just take the derivative, plug in 0, and I just get 1, which means the expansion for e to the x is 1 over k factorial, x to the power of k. Yes? And here is therefore our series. You can just write it as x to the k divided by k factorial. It will play a huge role in this class. We will not get into everything, but you understand, as you go into probability, you will see e all the time. It's your friend. So what you have here is, for example, if I have here 1 over k factorial, the summation of this series happens to be e to the power of 1, because here I just used x equal to 1 to produce the series, yes? If I plug 5, so basically 5 to the k over k factorial is e to the 5. If I plug minus 3 instead of the x, that's e to the minus 3. That's how it works, okay? So that in fact gives you an idea of how to calculate e to the x. And I'm not sure how you learned about it. This is the general situation. You can actually, without going through the way I derived the limit for e to the x, you can start with those equations. You can start with trying to solve the equation. The derivative of a function equals to the function, and the value of the function at 0 equals 1. What's the function? You will see that this is the infinite series that solves this equation. And then you can show that this series behaves like an exponential. Okay, so you don't have to, because exponentials are very weird. I mean, what are they exactly, right? So when you do it using the Taylor series development, you have this infinite polynomial, and then you realize that this infinite polynomial behaves like an exponential function. Partially because you see, you do things not always rigorously, but then you realize how to avoid mistakes. So your discoveries are always because you were daring. It's like the SAS statement, right? Their motto is "He who dares wins." So you dare, and then you can take your price. And then you try to realize why what you were doing is actually logical and why can you do it again and again. So this is something I leave you off. I actually wanted to write notes on it, but I ran out of time. So the question is, can you use this development? Can you solve this abstractly, get this formula, and figure out that it behaves like an exponential? Okay, and then you can define e to be the value of this function at 1. Good. So we are done for today. Next lecture will be probability. If you have any questions, you are free to stay. I will be happy to discuss those questions. You should have started chapter 1, and in other words, started homework for chapter 1 and solved quite a lot of problems. Good. All right. So I'm stopping the recording, and if you want to leave, then goodbye.